All right, last week in class. So this week we have a homework assignment due on Wednesday, although I may be pushing that considering how late we're getting to this LL parsing, and there are some LL parsing problems on the assignment. So I wanna make sure that those are possible depending on how far we get. I'll probably just push that to Friday. Then I'm going to spend Friday's class doing an exam for review. We're taking that during our final slot, which is Tuesday, 10:30 to 12:30. We'll probably take it, considering it's Tuesday. That's actually a good question. Whether it's going to be up in 301 or down here, considering it's usually like the beginning of the week, it might end up needing to be in here during that period. I will try to figure out if that room is free and let me know. Yeah, Tuesday at 10:30 is our final slot. It'll just be exam 4, so it'll be another typical exam. I'm not planning to make it any longer or harder. But it will not be cumulative, and so it's just another exam of the material we've covered since exam 3. I do have those exam 3s graded, but given our general lack of attendance in here, I figured it might be better to push going over that to individual questions in office hours. So if you'd like to see your score before I post it, go over any questions, argue for any points, feel free to see me after class, or if you're not free after class, you can come see me anytime that I'm here. I'll be here from about 12 to 2:30 today as well. Otherwise, I can even request a Zoom meeting and I'll try to have you read it. Whatever works. So I'm saying that I'm probably pushing the homework assignment till Friday. Because we haven't really gone over LL parsing yet. And I will reveal that last project in case people want to work on it. And if you submit both projects, I'll give you the score of the highest scoring one. And then I will give you half the score of the lower scoring one if you submit both as extra credit. So as soon as I get back to my office, I'm going to reveal that, but it's okay, we haven't been able to do it yet because we haven't gone over LL parsing. And then Friday's a review period for that final slot, which is really just exam 4. Any questions about calendar? What's coming up before we get started on LL parsing? Did you have a chance to catch up on I guess it was Wednesdays or Tuesday's lecture?
I forgot to watch it, so
Oh, no. That's gonna make this a little bit difficult to follow, I think, no pun intended, because we talked about first and follow functions. And those are going to play a huge role in answering the question of parsing in linear time. Because the goal is we talked about being able to answer the membership question in general in cubic time. But it turns out that there's a subset of those problems that we can answer in linear time. And that's the purpose of so knowing the first and follow functions, we can apply them to efficiently parsing what is going to be a significant portion of programming language parsing. So there's a little bit of preliminary work that we need to do, and that is to be able to convert a context-free grammar into a non-deterministic pushdown automata, which is something that I pushed off when we first saw it, saying that this is a process, but we actually need it in order to understand LL parsing. So this is exactly what LL parsing does. Going through this process will help us to understand exactly how LL parsing works. All right, so we're going to start with an NPDA. There are going to be 3 states. We have an initial state. The entire purpose of the initial state is to push the start non-terminal onto the stack. So the stack is only going to be non-terminals. Q1 is the state where all of the parsing happens. And then Q2 is going to be our final state. The transition from Q0 to Q1, all that does is push X onto the stack. So we have that rule, and that is consistent across everything. And then Q1 needs to be able to handle the following logic. For every reduction in the grammar, we want to replace the left-hand side with the right-hand side. Since it is a context-free grammar, we know the left-hand side is a single non-terminal. So we're gonna have a non-terminal on the left-hand side, and we're going to have some series or sequence of terminals or non-terminals on the right-hand side. So we're going to add a transition that says we're going from Q1 to Q1. We're going to pop nothing and push that left-hand side. So sorry, From Q1, it's not pop. We're going to make no transition, push an A onto the stack. No, read no input character. There we go. Read no input character, push an A onto the stack. Staying in Q1, then we're going to pop. I'm sorry. From state Q1, making no change to the input string, popping A off the stack. We're going to stay in Q1 and push this sequence of characters. So we need to look at the input string for the order that they appear in the stack. So when we see some kind of terminal, we need to map that to something. So for every terminal symbol, we're going to add an additional transition. From Q1, we're going to read that symbol from the input string. We're going to pop that terminal from the stack, and we're going to basically do nothing as a result. We're going to stay in Q1, not read anything. Stay there. So a transition from Q1 to Q2 can only happen if the input has no more characters and the stack is empty. So that looks something like this. I think it always helps to look at an example. So once people have written down what you think is important, we will roll on to the example. So we're going to have a grammar. We want to now create an equivalent NPDA that models the LL parsing process. So we start at Q0, pushing the start non-terminal onto the stack, and we're transitioning to Q1. So that looks like this. Remember that we don't have to draw the NPDA, and in fact, it was easier a lot of the time, considering how dense these NPDAs look, to just write the associated transitions. So we're making no change to the input. We're popping the bottom of stack character and pushing the S and the bottom of stack character, transitioning to Q1 as we do it. Question?
Sorry, I know I probably missed something, but didn't we already go over this, or is this review?
This is slightly different. I think we pushed exactly this one off, or we looked at it in general, but now we're modeling the LL parsing process. So instead of doing this as a general language, now we're doing it modeling a grammar. And the reason we're modeling a grammar is because we can now model it from a programming language's grammar, which allows us to parse that programming language in much more efficient time than we could with the general CYK that works for any grammar in Chomsky. So we're adding a transition rule for every production. We see that there are 4 of them, so this is all 4. Remember that when we have these comma separators here, they represent separate rules. So there's 1, 2, 3, and 4. And the reason we do it this way is because what goes on the stack is from right to left. So what's going to be on top of the stack when we're done is the first character that would appear on the string. gonna add some transition rules now that are going to take input symbols and shift them onto the stack. So we get something like this. Yeah, the final state transition, and we are done. So does anyone have any intuition about how this leads us to be able to model this grammar as an NPDA? Why does this work? So first and foremost, what's a string that's in the language?
C.
C is in the language. I love it. Coming up with something that's as simple as possible. So now rather than looking at this as a sequence of rules, I'm going to show us the NPDA so we can kind of visually go through this. So let's start with the stack. The whole purpose of this is we have our bottom stack character grade. We're going to push on our S as we transition from Q0 to Q1. But what transitions are we going through to be able to map this? What's the first transition we're going to see?
First transition to get C.
That we're gonna use here in order to be able to state that this is in a language defined by the grammar on the prior slide.
The one element 11 o'clock.
Yeah, this one right here. So this replaces an S with an A. So the stack at time step 2, I guess, would have the bottom stack character followed by an A, because we popped the S and pushed an A. What's the next one?
The far right one with the A and C.
Yeah, so we're going to now replace the A with a terminal C. What's the next rule?
Transition.
Close, not quite yet, one step away. Yeah,
The one at like 5 o'clock.
yeah, this one right here. What does this do? The intuition behind what this does? Besides just pop this C? What is the first element of it saying? So I'm gonna keep this here and draw another stack time.
It's like consuming the C from reading.
Consuming the C in the input. Yeah, remember that when we're reading this, we have some kind of current character, the position that we are in the string. This is moving past that and popping the C from the stack. So we end up now with our string pointer pointing off at the end of the string. So that, remember, this is non-deterministic. It's possible anytime we have just the bottom stack character that we can transition to this empty, to this final state. But only if we're at the end of the string do we accept. You have to have an empty stack when you do that. So if this were empty and we weren't at the end of the string, we would have no transition out of here and immediately reject. So because we're at the end of the string and we have an empty, then we are free to accept. Does that make sense? Now, what each of these transitions are doing, we have all of our making a move in the grammar, replacing the left-hand side with the right-hand side, and all of our consuming characters in the stack and consuming them in the string. So that is how we are going to think about this process of transitioning from context-free grammar to an NPDA. So what would it look like to model A, B, C, A, B. Note that we have a look ahead character. That's one other thing we're gonna need to store when we do this. Because if we look back at our grammar. Let's say we see an A in the string. Is that an A from here? Or is that an A from here, or an A from here, or an A from here? B from here or B from here? We need to know what character we are looking for next. This will help us when we have ambiguity in our grammar. Here we don't have an ambiguity. But as soon as we start having two different productions that start with the same terminal, we want to avoid a search. Right? We don't want to have to figure out, okay, which one of these productions do we want to apply? So here's what that would look like. So the look ahead just tells us the next character that we're looking at in the string. And eventually we're going to try to figure out how far ahead do we need to look to figure out which production we need to apply. So that's where we're going next. But we see the next character is an A. So if the next character doesn't match what's here, we just reject. If it's a terminal. That allows us to stop early. So we push the S, since the look ahead is an A, we're going to now replace that S with ASB. Because remember, S could move into capital A, or it can move into a capital SB. Which one do you want to apply there? Yeah.
So a look ahead of one is just like normal one rewrite head.
Kind of, it's a look ahead of one in the string telling us that we'll always be able to determine which production to apply as long as we know the next one character in the string. So certain grammars will have that rule where we only need to look ahead one. As soon as we look ahead one, we know which character we need to apply. And that will apply the first and follow functions that we talked about last time. Because we need to know what is the first character that a non-terminal can produce. We need to know after a particular non-terminal, what is the first character that could follow that. Both of those will help us to remove that ambiguity of which production to apply. So that you can see how this is linear. In that we're only making a couple of changes to the stack for each character that we are reading in the string. Rather than something as gross as CYK, or even worse than that, something that's brute force, where we have to go search for which production to apply. If we've done that work ahead of time to fill in first and follow, then we can actually do this reasonably. Luckily, we don't need that for this example because this is an LL1 grammar, meaning that we only need a single look ahead to determine which production to apply. As soon as there's ambiguity, we need to consider the first and follow functions. So first and foremost, does this logic make sense? Does what's happening here, I can gladly go over this in more detail, if that would be helpful. So this tells us the state of the NVDA, the next character that we're reading. So we know that as we transition from state Q0 to Q1, we push the start non-terminal. After this, we need to figure out, all right, what production are we applying? Are we going to capital A or are we going to a capital SB? For now, I'm just leaving this as we don't know. Use your logic to figure it out. Well, capital A can only become something that starts with a B or something that starts with a C. Since the next character is an A, we should apply ASB. So that's what we're going to do in reverse order. We're going to push them to the stack, B capital S A. Now, since we have this A, we can move ahead in the string. So instead of pointing here, we're pointing here. Now we're looking for a B. So using S, we can now see that the only way to produce the next character being a B is to replace that S with an A. And then change that A into B capital A. So that's exactly what we're going to do over the next two steps. Now on the top of the stack, we have that B that we're looking for. So we can move forward from B to C as we pop that B off the stack. Now we know that capital A can also produce a C, so we're gonna go down that route. We're gonna replace the capital A with a C, because that was a rule we could use in our grammar. Now we can consume the C. Now we can consume the A. Now we can consume the B. Now we have an empty stack, and we're at the end of the string, so we can transition from Q1 to Q2. The look ahead is the end of string character that we talked about in the follow function. And we can now accept and say that this string is in this language defined by this grammar. If we ever had a look ahead that was not this character, two things could have happened. We applied the wrong grammar rule, or the string's not in the language. Questions on this? Does the process make sense? If I gave you a language and a grammar, would you be able to go through a process like this to produce a series of stacks in time to go through modeling that conversion? All right, so from this, we can build what we call an LL1 parse table. We're going to now start looking ahead and storing those look aheads in a table. As we do this, this will tell us which rule to apply rather than having to look at it in logic or guess or search. So, as in any table, we're going to have two dimensions. The row dimension are the non-terminals in the grammar, and the column are all of the terminals in the grammar plus the end of string marker $. How do we fill out the table? We're going to call this LL of row column. So it's an LL table. So LL is the name of what we're going to call a two-dimensional array or a matrix. And we're going to fill in at row, row, and column, column. For every production, we're going to look at each terminal in first of the right-hand side, adding the right-hand side to the table in LL of the left-hand side, comma, that terminal. I know that's a bunch of gibberish, and we'll get to an example of that. There's logic behind this. So we're going to start using the first function that we calculated. So step one is going to be calculate first of everything. Once you have first of each non-terminal, then you can start applying this and looking this up. The trick is, of course, if lambda appears in the first of the right-hand side, then we need to add the entire right-hand side to the LL table at row, left-hand side, column, that element, for every element that is in the follow of the left-hand side. So we also need to calculate follow for every non-terminal to be able to go through this process. If there's an empty entry in the table, that is something that we do not allow. I mean, we cannot, from this state, produce this look-ahead terminal that we are looking for. If we're trying to find a B and say which production produces a B from our current state, if no such production can produce a B, this entry in this table of the current non-terminal we are on, the column being the terminal B, then that means this grammar cannot produce that from this non-terminal. Let's give you an example, because that was a lot of logic. So we're going to go through this exact same grammar that we were using, and we're going to first calculate first and follow. Do we remember how to do this? So let's start with, I think it's easiest to go with first of A. First of the non-terminal A. What are all of the terminals that could appear as the first terminal after resolving the non-terminal A? That's going to be a set of some number of terminals that is in this alphabet. B and C. yeah, if we're trying to resolve an A, we can either apply this rule of which the first terminal is a B, or the first terminal is a C. So first, let's go ahead and write this out. First, we're going to do S and A, and then we'll have a follow. S and A. All right, so we said A was just the set BC. How about first of S?
Maybe
ABC, how do we get there?
the A is from the ASB, and then the BC comes since A. on its
Yeah,
own.
we can produce A, because we did this first, we can now just union that. So we know that this is basically going to be the set that contains A. Union the set that contains everything that is first of A. So I should really call this first of A, but I'm just gonna shorthand. And say we union these together, and so we get the set ABC. That tells us that any of these characters can actually start a string in the language. There's at least one string that starts with each of these characters in the language. Excellent. How about follow? This is saying that wherever S and or A appear, what is, after we resolve that, what is the next terminal that could apply? So if there is a capital A, what could follow capital A?
Is it just a little bit?
There's little a, but there's one more thing. Could it end the string somehow? If we go S to A, and then we resolve that somehow, what comes after this is the end of string marker. So we need to include that end of string marker in any follow set. And we said that for S, S always contains the end of string marker, because it is by definition the start non-terminal. When we have a string in that language, by the time we've resolved S, what's done with that is the end of the string. So S always has the end of string marker. But what could follow an S besides the end of string? A B. In case we did S arrow A capital S B, we resolve this S, and B could be the next character after we do that. So B is going to be here as well. And I realized that I probably should have some kind of consistent notation for where that dollar goes, but yeah.
Isn't A also in follow S? Little a,
Because S could become A, and when we resolve that A at the very end of that. I don't quite see it. So give me, if that were to be true, you would be able to start with S arrow something. And be able to produce something that said. Somehow we would have an S followed by an A as something, some part of some string. In some sequence of this. What would the set of productions be to generate this? Somewhere in the string.
I think I had it mixed up.
Yeah, you're right. It's not S, it's A, isn't it?
Yeah, so it's not that,
Yeah, it's A with a B.
yeah, it's not that. A should be an S, it's that S should be an A,
Yeah. Yeah,
because
you're
N is
right.
the
You're
non-terminal.
absolutely right. So can A be followed by a B somehow by some sequence of productions? The answer is yes. How?
You go from S to ASB,
So S arrow A S B,
and then turn that S into an A.
yep. A B, and now we have it. So this tells us that B should be in this set. Yep.
When you write that out, you're kind of like union a bunch of things together.
Yeah, so if we want to go by our follow rules, let's look back at the actual process that we go through to calculate follow. What was that process?
When the terminals immediately following non-terminals, essentially.
Yeah. So we kind of logicked it, but now imagine we had a grammar with 70 productions. That's gonna be really gross to think about and do by hand. So it might make more sense to have some kind of algorithmic process for it. Yeah,
I think it's mainly two rules, so like. The first scenario is if you have a non-terminal following, or if you have a terminal following said terminal on the right-hand side, that's in it, i.e. the B follows the S, the A follows the A.
yeah,
But then the other thing is. So if the right hand ends in a non-terminal, i.e. S to A. Everything in follow S is in follow A.
yeah. So since we hadn't done follow S yet. We couldn't go to it. We should have paused there, finished follow S. And then union follow S into follow A. So we can see that A can directly produce A and A can directly produce dollar, but A can also produce whatever S can produce, because we can go directly from S to A. So we should have paused there, finished S, and then union this with that result. All right, now that we have the first and follow. Anyone with questions on that process? It was absolutely right, it was even in my slide. We can now build this LL parse table. So for every right-hand side of a production that starts with a terminal, we're going to add it to the left-hand side, the row left-hand side, the column, first symbol of right-hand side. So this table is going to look like. We have S and A, and we have A, B, C, and dollar. So in this grammar, we're going to look for every pair of left-hand side, right-hand side that starts with a terminal. So we're going to add the production to each of these cells. So we can get from S to A via ASB. We can get from A to B via BAA. We can get from A to C via C. So you're just going to do one pass through the grammar. And you're going to say for every production that meets this form, we're going to add it to the table. Add the production to the table, that is the left-hand side to first terminal of the right-hand side for every production that starts with a terminal. Then we need to go through and look at everything that starts with a terminal. So now we're going to have to do some fun for this right-hand side. Since we derive it from S, we're going to add it to LL of S, comma, X, where X is every element in first of A. So first of A is going to be this lookup to this cell in our first table. We're going to say S arrow A can produce every element of first of A. So we can get from S to B via the production A. We can get from S to C via the production A. Does this make sense? What does this table tell us? Just kind of intuitively.
The possible moves at a given time.
Yeah, if we have a non-terminal at the moment, we can do a lookup and say, can we get to a state where we can produce this character, as well as how many different productions are there? Note how there's only one element at each of these locations, but really each one of these cells is a set. Not a single element, because you could have something that allowed us to directly produce B. And now we don't know if we're just looking at the top of a stack. We see a B. Do we apply this rule or do we apply this rule to get there? Does that make sense? We have some ambiguity. How would that ambiguity be apparent in this table? How would this table change to allow for this extra rule? We add an extra rule right there. But looking at this cell, because there are multiple productions in this cell, that would tell us if we reach a position where we're looking at the left-hand side is S and the look-ahead character we're looking for is a B, we need more of the string to figure out which production to apply. We need to apply a look-ahead of more than a single character. Because if we looked ahead and saw, there'd be a few options. We could see BB, we could see BC, or we could see B followed by the end of string. Right, does that make sense for a two-character look ahead? If it's BB, then we can't just apply the B here that ends the string. We have to do something that continues the string, so that tells us to apply this capital A, because now we can produce B capital A, which can become B capital A, so we can produce BB from that. We could produce BC from that, but we could not produce B dollar directly from capital A. On the other hand, this B ends the string, so if we see a two-character look ahead that says B dollar, now we need to apply this rule to that. So you can see that depending on, once you construct this table, the table tells you where the ambiguity is. Now the question is, how far ahead do you have to look to resolve that ambiguity? So that's where we're going to go. Now, so here's the table. Does anyone have any questions about producing the table, reading the table? The concept of ambiguity in that table, if there's more than one element in any of these cells, you can't tell with a single look ahead character which production to apply. So LL1 is a process that is going to read from the LL1 table and do the following. all we need is a method push that takes a string W and pushes it onto the stack from the rightmost character to the leftmost character. Touch the. We've reached winter, everything shocks everyone. We just need top. Just like a stack's top returns the top symbol of the stack without popping it. We need pop, returning the top symbol of the stack and removing it. Get tells us the next look ahead symbol in the input string. And that's it. That's all LL1 is going to contain. How do we know when we're done? We terminate with this concept of accept, meaning that we're in the appropriate state of the NPDA, strings the language. If we terminate with the concept of error, then the string is not in the language. So the entirety of the algorithm just looks like this. We can see how we can map exactly this logic directly to the concept of the NPDA, to the logic of the grammar. It all works in tandem. So push S is that transition from Q0 to Q1. Everything else, until we reach the very end, if look ahead is not S, then error else accept. That's the concept of Q2. Everything in between is the concept of Q1. While the stack is not empty, do a bunch of stuff. Everything that is in there is one of the possible transitions out of Q1 in the NPDA. Except that, rather than going through that transition process, now we're going to be looking at this LL table. Because instead of having to do a look ahead, or trying to figure out what's possible, if the LL table doesn't have any ambiguity in it, then we apply the associated rule based on a lookup to the table. So the preparation for this algorithm is calculating first, calculating follow, and populating the LL parse table. If you do those three things, then this is a linear time algorithm. Question?
Wasn't this algorithm one of the final projects?
It is.
Interesting.
So note that I'm giving you the logic here as pseudocode. I'm not telling you it's in this, all the logic is in the slides for the first, for the follow, for the table, and then applying this algorithm. So putting all of that together into one project is all I'm looking for. Yeah, and I will reveal this slide. You will have this available to you for that project.
Yeah, before I forget. Our final, is it Friday or during the finals period?
Finals period.
Okay.
We're doing a review on Friday. I figured if people probably would prefer to have a little bit more time to prepare. If anyone needs to head out and wants to take it on Friday, I'm open to that. Let me know if you have a schedule conflict to work with you. All right, so what does it look like? Same grammar as before, so we still have that grammar. We're gonna use that same string, ABC, AB. We can show the contents of the stack and the look ahead at each step. So it ends up looking something like this. So we start, we're going to push S onto the stack. We know our lookup table. So when we see that we're trying to produce an A as the next character and we have an S, we're looking at row S, column A in our LL table. The only production that was there was ASB. So we're going to push those onto the stack from right to left. Now the look ahead character matches the stack character, so we can pop. Moving ahead. We see that we're at a non-terminal S trying to produce a B. That's a lookup into the LL table. The only production that is there is A. So we're going to replace that S with an A. Now, we're still trying to look ahead to the B. So we're in the table, row capital A, column B. And that production was B capital A. So we're going to push those onto the stack from right to left. Getting B capital A. We can now map the look ahead to the character. So we move forward. We're now looking to produce a C. But we have this capital A. So we're going to look at the LL table, row capital A, column C. And we see that there's a direct rule that replaces the capital A with the C. So we're going to do that in the stack, popping the A, replacing it with a C. Now we can see that we immediately pop off the C, mapping it there, the A mapping it there, the B mapping it there, hitting an empty stack, and the end of string character, so we accept. So all of this is modeling what we did with that context-free grammar to NPDA. But now we have the table produced from the concept of the first and the follow. What do we think? Questions on that? Algorithm makes sense? So there's a little bit of prep to do, but once the prep is done, it's really fast. The issue arises, just as I mentioned, when there's ambiguity in that table. Not all grammars are LL1, which means we need to look ahead more than a single step to know which production to apply, which means that we need to think of a longer look ahead. Some grammars, in fact, are not LLK for any K. So how do we do things like determine the membership problem for an LL, for a grammar that's not LLK for any K? What happens then? We're forced to use CYK, basically. So any LL of some constant look ahead K, we can produce an LL table for, which means we can determine the membership in linear time, which is amazing. So how do we determine that a grammar is not LL1? We look for a conflict in the LL1 table, just as I mentioned. That means that there's some cell in that matrix table 2D array that has more than one right-hand sided. So with the last minute, let's see if I can give you a quick example. This is going to be a little bit big. So I actually want people to go through and get experience with this. So I think we'll come back and do this tomorrow. So this is where the learning part ends and the application part begins. I'm actually going to have you go through and produce what the LL1 table would look like for this. So you would, if you want to get started on it and see if you can make some progress on it, then you would start with calculating the first and follow for S, and then go into the LL table. Yeah,
The final project, is that for LL1 or for LLK?
I believe it's just LL1.
Good.
Yeah, and just like the other project, I have input, output, I have the ability to test a couple of test cases for you to verify that things are working. So to recap the announcements for those who walked in a little bit late. I'm pushing the assignment from Wednesday to Friday, just so that you have as much time to get everything done, because I know we're just going over LL parsing now. You can probably do a little bit more with the assignment, but I don't really like pushing it into a couple of days. I know that creates a ton of deadlines for Friday. But there's not really enough time left to do anything about it, and I want to give enough time for you to study for and do well on the final, and I don't want to make things due after the final exam. That seems kind of bad of me. So everything's due on Friday, the assignment, the project. You need to do one of the two projects, but if you do both projects, I said I will give you the credit of the better scoring project as your project score, and I will give you half the credit of the other one you produce as extra credit. The project is worth quite a bit, so that's going to end up being a very reasonable curve if you are able to get both projects complete. I will be around all week to help you get that in shape. Then we will review on Friday for Tuesday's final, which is not really a final, it's really just exam 4. But I'll give you the 2-hour slot. I'm writing it to take an hour, but as we know with me, sometimes that hour is really pushing an hour. I also have your exam 3s graded in my office rather than going over them in this class. I really wanted to spend some time to get you prepared to start working on the project. I'm happy to go show you that exam in my office, go over it, listen to any concerns you have about the grading, argue for some points back, go over any of the problems you want to see. So I'll do that in office hours. All right. I'm headed there now. So you can follow me up there if you have time. If not, I'll be in my office from about 12 to 2:30 today. Or any other time this week. For that.